Hi, and welcome to 6.1 Universal Gravitation Calculations. In this homework assignment, we use the Newton's Law of Universal Gravitation formula a lot, and we practice plugging in the numbers correctly into our calculator. As you could see, it says be sure to use parentheses or the E button when performing calculations in the calculator. You want to make sure you're being careful because there's going to be a lot of scientific notation that we have to do. So let's get right into it. It says two 2 kilogram balls are placed with their centers 7.25 meters apart. What gravitational force exists between them? So this is the situation. 2 kilogram balls and their centers are 7.25 meters away from each other. There's a force due to gravity, equal and opposite, that acts between them. All right, so we could let me try to fit it in here. Fg is equal to G m1 m2 over r squared. The force due to gravity is directly proportional to both the masses and inversely proportional to the square of the distance. So that means as the mass, one or both of the masses increases, the force increases. As the distance between the two of them increases, the force decreases. It's an inverse square relationship. Why is this called R? A lot of times you're going to have like a planet and a moon, or a star and a planet, and they're orbiting each other, and the distance between them is the radius of that orbit. So they just stick with the R instead of distance, because you could think of it as a distance between the two centers. The reason they call it radius is because a lot of times these things are in orbit around each other. So let's plug in some numbers. So the first thing you see is this big G. That's the universal gravitation constant. It's just a number, and you look up the number in your reference table, and the universal gravitation constant, it's the first one. We're going to be using this a lot. 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. 6.67 times 10 to the negative 11. So you plug that in here. Newton meters squared per kilogram squared. I'll show you where that unit comes from. So this is 2 kilograms. This is 2 kilograms. And the distance between them, or the radius, 7.25 meters. And that gets squared. So the first thing you might notice about that universal gravitation constant, besides the fact that it's this weird scientific notation, is that it also has these weird units. Where did these units come from? Well, if you look, you have a kilogram times a kilogram, which is a kilogram squared. So if we rewrite the units up here, this has nothing to do with how to do this problem, by the way. I'm just kind of teaching. So kilograms times a kilogram. This becomes a kilogram squared. And the kilogram squared cancels out with the kilogram squared. You're also dividing by a meter down here. That's getting squared. So that meter squared gets canceled with that meter squared. What are you left with? Newtons, which is what we're solving for. A force due to gravity. So now we know kind of where the units are coming from. Let's plug this into our calculator, and let's be careful when we do so. It says use parentheses or the E button. I prefer to use the E button personally. I still put everything in the numerator in parentheses. So here's how you use the E button. You just type in the first number, 6.67, and then you do second, here's the E, that double capital E. You only have to press it once. That E just means times 10 to the. And then you type in the exponent, negative 11. Let me show you on the calculator what that is. Okay, so it's going to do that. I could do the same thing, 6.67 times 10 to the negative 11. So you could replace this E with times 10 to the. You're just writing the first number and then the exponent when you're using the E button, and you end up getting the same thing. Okay, so here's how you do it. 6.67 E negative 11 times 2 times 2. End the parentheses, we're done with the numerator, divided by, open parentheses for the denominator, 7.25 squared, close parentheses. You get 5.07, 5.08 times 10 to the negative 12. So FG equals 5.08 times 10 to the negative 12 newtons. All right, so that's your answer right there. That's the force of gravity. Pretty big number, right? Wrong. It's a tiny number. The gravitational force isn't that strong, especially between two 2-kilogram balls like that. All right, you need a supermassive like planet or moon to get a noticeable force due to gravity. Number 2, what is the gravitational force between two 8-kilogram spherical masses that are 5 meters apart? What is the gravitational force between them when they are 5 times 10 to the 1 meters apart? How are these values related? Okay, so let's do the same thing again. Fg is equal to G, m1, m2 over r squared. Fg is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times, they're two 8-kilogram balls, divided by 5 meters squared. Fg equals, again, this is a calculator heavy thing, so I'll just show you how to do it. Now, I'm going to not use the E button just to show you what you would have to do instead. All right, so you open parentheses, 6.67 times 10 to the negative 11. Technically, if you're being paranoid, you want to put all of these scientific notation things in parentheses. So each one gets their own set of parentheses. Times 8, end parentheses for the numerator, divided by, and then when doing these problems, I always just do the same thing. I put the numerator in parentheses, and I put the denominator in parentheses. So I get 1.71 times 10 to the negative 10. 1.71 times 10 to the negative 10 newtons. Now, let's see what happens when we separate them by this different distance. I'll plug it in. Okay, so as you can see, the only thing that's different is the radius is 1 power of 10 larger than it was before. This turns into 50 meters instead of 5 meters. So let's see how that affects the weight, the force due to gravity, when we're plugging this in. Now, we're going to do second entry. We come over here. I mean, you could type everything back in again, but why bother? Your calculator is a powerful tool. Might as well use it to the best of its abilities. And let's see. Deleting all this stuff. Okay, so now we have 5.0 E1, and we want to square that. And if we wanted to, we could even put the denominator in parentheses like this. Insert a parentheses. And let's see, what do you think is going to happen? Is it going to be a power of 10 different? Or is it going to be more or less? Let's see. 1.7 times 10 to the negative 12. Not just 1 power of 10, but 2 powers of 10, because it's the radius squared. It really does affect the weight, because it's a squared quantity. So you get 1.71 times 10 to the negative 12 newtons. Okay, so you could say 2 powers of 10 smaller. Okay, if you increase the radius, it gets 2 powers of 10 smaller. All right, now 3. The diagram shows spheres A and B with masses of m and 3m respectively. If the gravitational force of attraction on sphere A on sphere B is 2 newtons. So here, this is the force. What is the gravitational force of attraction of sphere B on sphere A? It's exactly equal to each other. F. Right? Oh, no, wait. What do they say? 2 newtons. So they're telling you that this is 2 newtons. So Fg equals 2 newtons. That's the answer. Here's why. You could say Newton's third law. Every action has an equal and opposite reaction. But that's kind of glossing over what's really happening here. There's a good way to explain this here. So here, let's just say we have a mass and another mass. This is Fg. Let me use a different color here. Let's see. So this is Fg. Hold on. So here's what's going on. We have, if this was one mass and this is another mass, this one is attracted to this mass. Let's just say they're both one mass for now. Now we have a second mass. This is more massive. This mass over here is attracted to this mass. And this mass over here is attracted to that mass. Right? So this one was attracted to this one. Now this one is attracted to this one and this one. This guy is attracted to this guy, and this other guy is attracted to this guy. So you can see the forces, they balance out. I have 2 force vectors on both sides. Let me add that third m. All right? Let me add that third m. So this is attracted to that. This is attracted to that as well. So you could call it like 3 force vectors here and 3 force vectors here. All right, so they end up having the same force due to gravity acting on them. So if one is 2 newtons, the other is also 2 newtons. And the quick way to say it is just, because of Newton's third law. But that's kind of why as well, a different way to think of it. All right, number 4, 2 spheres are a certain distance apart. Sphere A, so now let me do it like we did all of the other problems. I'm going to write down the given information. So sphere A has a mass of 8 kilograms. Sphere B has a mass of 6 kilograms. Sphere A exerts a gravitational force of 5.08 times 10 to the negative 12 newtons on sphere B. What is the distance between the 2 centers of the spheres? Here, they're looking for the radius, not Fg. You have the 2 spheres, radius. That's what they're looking for. They tell you, and again, Fg is the same. They tell you what Fg is, and they tell you what the masses are. So we're looking for the radius in this case. So you plug in, you write the equation. Fg is equal to G m1 m2 over r squared, and you plug in what you know. Don't forget, in this case, you know what the weight is. So you got 5.08 times 10 to the negative 12 is equal to, G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. I didn't write it on the side, so let me write it on the side with the units. That way I get full points for writing my units out. And the mass A is 8, mass B is 6. We're looking for the radius. So you got to do a little bit of math here. The first thing I would do is find out what this term is, because I like to cross multiply. All right, or you could multiply by the radius squared on both sides, whichever way you like to think about it. That's the way I was taught. So that's always kind of the way my brain goes. So whatever works for you. So we're doing the numerator first. We're doing this and figuring out what that is. 6.67. Oh man, hold on. 6.67 e negative 11 times 8 times 6. That gives you 3.2 times 10 to the negative 9. So now, after you cross multiply, you get 3.2 times 10 to the negative 9, 5.08 times 10 to the negative 12 times r squared on the other side. So now you have to divide both sides by 5.08 times 10 to the negative 12. So you get r squared is equal to 3.2 times 10 to the negative 9 divided by 5.08 times 10 to the negative 12. And you could do the square root of the whole thing. Let's just plug that in our calculator, see what that looks like. All right, so the square root of our answer, now I won't do it that way, because that would be too easy. All right, so open parentheses, 3.2 e negative 9 end parentheses divided by 5.08 e negative 12 gives you your answer 25.1 meters. Now I'm going to show you something on the calculator here. This is where it gets important. I was being a little paranoid by putting the scientific notations in parentheses. Technically, when you do this, you should, even without the scientific notation, the E button tells your calculator, listen, I'm doing times 10 to the, and your PEMDAS better not mess up what I'm trying to do. I'm doing scientific notation, so just make sure you do what you're supposed to. It should give you the same answer, and it does. What will mess some people up is if you try to do 3.2 times 10 to the negative 9 divided by 5.08 times 10 to the negative 12. To us, it looks like it's the same thing, but to your calculator, it's going to do, let's do the PEMDAS with the calculator. It'll do the square root last. But first, it's going to do 3.2, take that number, multiply it by 10 to the negative 5. Then divide that by 5.08, and then multiply the whole thing times 10 to the negative 12. All of a sudden, the 10 to the negative 12 is in the numerator, not in the denominator where it belongs. We should get a different number. And we do. It's way off. Look at that. Off by a power of 10. It's crazy. Here's what you could do. If you really don't like the E button, here's a different way to do it. If you're going to use times 10 to the, you got to plug everything in parentheses. Times 10 to the negative 9. Before I got used to using the E button, I would keep doing this, but, I got into the habit of putting everything into parentheses, which is sometimes why I say I get paranoid, and I even though I use the E button, I still use the parentheses just because I'm like, well, it won't hurt. Might as well do it so the calculator knows what the heck I'm talking about. And it's not, you're right, it's not going to hurt. I'm talking to myself now. You get the same answer, right? So if you're not going to use the E button, if you're going to do times 10 to the, it's super important you put them in parentheses. You see the difference between the two? Hopefully. That's the whole purpose of this homework, is to get used to using the calculator. I know you know how to use the formula. And then there's the other thing with, this is a weird constant to use, but, it's just a number. The tricky thing is plugging it in the calculator. Number 9. 2 satellites of equal mass are put into orbit 30 meters apart. The gravitational force between them is 2.0 times 10 to the negative 7 newtons. What is the mass of each satellite? So they're looking for the mass. They're equal masses, which makes it a little bit easier. The radius is 30 meters. The force is 2.0 times 10 to the negative 7 newtons. While I'm writing down my givens, might as well do this. So I get full points for units. And that's all we got. So what is the mass? Let's write our equation. Fg is equal to G m1 m2 over r squared. So 2.0 times 10 to the negative 7 is equal to 6.67 times 10 to the negative 11 times, what are we going to plug in? Should we call it m1 and m2 still? They're equal masses. So instead of m1 and m2, I'm just going to do m times m. Remember, they're multiplied by each other. Divided by the radius, 30 squared. So we could rewrite the whole thing. I want to change this. Let's change it. So now you have to ask yourself, what is mass times a mass? What's m times m? M times m. Or x times x. Or n times n. This is going to be equal to x squared, n squared, mass squared. And that's the main trick for solving this one. Everything else is pretty much just algebraic. So you do 2.0 times 10 to the negative 7. See, I'm going back to my old ways. Times 30 squared. In this case, it's not going to matter. Sometimes it doesn't matter. Sometimes it does, mostly when you're dividing. As you can see, if I did put parentheses in here, if I did put some parentheses in here, you'd get the same answer because your calculator just does PEMDAS. So sometimes PEMDAS does what you want it to do, sometimes it doesn't. Best practice is to either just put everything in parentheses or use the E button when doing scientific notation. So that's 1.8 times 10 to the negative 4 is equal to 6.67 times 10 to the negative 11 meters squared. So this is 1.8 times 10 to the negative 4 divided by 6.67 times 10 to the negative 11. So the meters squared is going to be equal to, well, you just take this and divide it by, you could do 6.67 e negative 11. Or you could do in parentheses. So then you get the meters squared is equal to this huge number, 2.7 times 10 to the 1, 2, 3, 4, 5, 6. 2.7 times 10 to the 6. But that doesn't really matter because we want to know what the square root of that is. What is one mass equal to? So you take the square root of your answer, second answer. You guys know you could do that, right? Some people don't. And it's where the negative is, second answer. You get 1,643 kilograms. So that is the mass of one of the satellites. All right, and then the other satellite is there. The same. Number 6. So, yeah, you can see you rerounded. Oh, nice. I put an answer key at the bottom of this. Beautiful. The mass of an electron is 9.1 times 10 to the negative 31 kilograms. The mass of the proton is 1.7 times 10 to the negative 27 kilograms. They are about 1 times 10 to the negative 10 meters apart in a hydrogen atom. What force of gravity exists between the proton and the electron of a hydrogen atom? So you just write down all your given information, just like that, so you get full points for units. This is the mass of the electron, mass of the proton, the distance between them, and the universal gravitation constant. They're asking for the force of gravity. This is an interesting question, and we do it again when we do electrostatic forces. So not gravitational, but electrostatic. So there's these two different non-contact forces, and it's a way to compare how strong gravity is compared to how strong the electrostatic forces. So instead of mass, we'll have a charge, and we use a lowercase q for the charge. There'll still be a radius, and then there's this electrostatic constant k instead of the gravitational constant. And then you use that to find Fe, the electrostatic force. But it's getting way ahead of ourselves. We're still doing gravity, not really electrostatic, so we won't worry about that yet. We just write our equation, then we substitute what we know and what we don't know. Don't forget to square the radius. And that's technically the easiest part, even though we're writing a lot. The hard part for this is plugging it in the calculator. So again, we just want to be careful when we're plugging it in. So you just take it one step at a time. First you do the universal gravitation constant, and I open parentheses for the numerator, 6.67 times 10 to the is the E button, -11, times 9.1 E -31 times 1.7 E -27, end parentheses, that's the end of the numerator, as you can see, divided by open parentheses. Now, since we're going to square this guy, I like to put this like that, 1.0 E -10, close the parentheses, square it, close the parentheses for the denominator, equals 1.03 times 10 to the -47. Newtons. Okay, very good. Now, one thing to note, sometimes instead of plugging in this 6.67 E -11, some of the newcomers to the E button will still try to do this. They'll do something like 6.67 E to the -11. Now that doesn't make sense. No, that's not what we want. And then sometimes people do, what's the other one I see? 6.67 E 10, and then they'll just do it anyway, 10 to the -11, like that. And then you get 0. I don't know. There's a lot of wonky stuff. Just to reiterate, here's how you use the E button. 6.67. You put in the first number, then you do E, then you do the exponent, and that's it. You're not typing in 10 or times or to the. All right, the E means times 10 to the, so you just need the first number, E, and then the exponent for the scientific notation. Okay, have a good day.